Welcome again. Here I want to discuss about one-way ANOVA, what it is, where it is applied, and how it can be applied. ANOVA is nothing but analysis of variance. Analysis of variance means comparing two variances, whether these two variances belongs to the same source or belongs to the different source. Suppose variability of one mobile battery's life compared to other mobile's battery life. So if we have to compare these two variability, whether one product is good or the other product is good. Here good does not mean the average battery life. Good means what the life they are claiming, then every product has a precision of occurrence around that value. So in that case, we have to compare that with how much variability one product has compared to the other product. For this, we basically perform F-test hypothesis, which is based on F distribution. In F distribution, F is nothing but a ratio of two variances. So I'll move further. I can say that ANOVA is a combination of multiple F-tests, where we want to see the effect of one or two variables on the response variable. So ANOVA is to find out the effect of independent variable versus response variable. We are also call them dependent variable. So this is what the relationship is. So there are certain terms you want to develop the relationship, the effect of independent variable on the response variable. So response variable is basically a measured output. Independent variables are factors which we can change, factors where we can change the different levels and we can perform the test. For example, there are n number of machines and they are producing rubber stamp, and the tensile strength of the rubber is being tested. So every machine has a number of lot of rubber stamps produced. So every lot has certain tensile strength values for each rubber stamp produced. So machine number or type of machine may be automatic, may be semi-automatic, may be fully automatic, maybe type 1 from one manufacturer or to second manufacturer, third manufacturer, fourth manufacturer. Anyway, there are different machines producing the same item. So if we want to see the variability among the different production process, so that we can judge using ANOVA analysis. So machine is a machine number, machine name, machine value can be a input variable or independent variables, which can have different labels. Here labels are machine. And nowadays corona effect is very common. So we can say that if we are testing the killing of the virus at 20 degrees centigrade, 30 degrees centigrade, 40 degrees centigrade, 50 degrees centigrade, 60 degrees centigrade. So these are levels of the temperature at which we may perform the test. And we want to see at what level most of the samples given having coronavirus have been killed. So that way we can apply ANOVA analysis. At each level, when we perform different experiments, these are called replications. Different samples testing at one temperature is replication of the experiment. If there are suppose two variables, for example, we want to see the effect of temperature as well as the effect of pressure. So in both the cases, then there is a possibility of interaction effect. Interaction effect means the combined effect of pressure as well as temperature may not be the same as the effect of temperature plus pressure. It may be higher than that sum or lower than that sum. So that is what we call interaction effect. So in ANOVA analysis, we can perform the F distribution test, F distribution hypothesis to see different types of effect, either main effect or the interaction effect. If there is one independent variable, we call it one-way ANOVA. If there are two independent variables, we call it two-way ANOVA. If there are three independent variables, we call it three-way ANOVA. If there are more than two response variables, we call it multivariate analysis of variance, what is generally known as MANOVA. Multivariate analysis of variance. So before going for this hypothesis of ANOVA analysis, I want to bring you to the place where I want to explain what is ANOVA analysis. For that, first read a sample example. Read this sample example. This is a problem which we will take up so that you can better understand what ANOVA analysis is. 6 different machines are being considered for use in manufacturing rubber seals. The machines are being compared with respect to the tensile strength of the product. A random sample of 4 seals from each machine is used to determine whether the mean tensile strength varies from machine to machine or not. So the following data is given to you. For first machine, there are 4 sample tensile strength measured. For another machine, again 4. For another machine, again 4. Then for 6 machines, we do have 4 sample values. What ANOVA will do? ANOVA will tell this among these 6 machines whether the output has a similar or same tensile strength or the different tensile strength. That is what is the basic aim or the basic question which we try to solve using the ANOVA analysis. So keep this problem in mind as I will move further for the explanation of what ANOVA is and what it does. So this is machine 1, machine 6. Now the observed value we refer as Y. Y is nothing but the value for tensile strength, which we measure here. So the first value may be Y11, Y12 and so on up to Y1n if there are n replications. There are 4 in your example, Y21, Y22, Y62 and so on, Y6n. So now out of this, we can take the total of this. If suppose total, this is Y1 dot, this may be referred as Y2 dot, Y3 dot and so on, Y6 dot. This is what we may call total value, and if suppose I calculate mean, so this will be Y bar 1 dot, Y bar 2 dot, Y bar 3 dot, so on, Y bar 6 dot. If we take mean of all, that will be Y bar dot dot, which will be nothing but summation of all Yij. I represents the machine number, J represents your replication, divided by number of machines, for example 6 here, and number of replications. So the main question here is to see the effect of machine on tensile strength. This is the question which we have to answer. Now in ANOVA analysis, what we do is basically we want to see if there is an effect of machine on tensile strength. It is given in kg per centimeter square. This is given as a number. So machine 1, 2, 3, 4, 5, 6. Now at every point there are some set of values. When we have every set of values, now we can perform a regression analysis. If you perform, suppose, linear regression, then we can have a line over here which can give us a estimated value of y bx plus a. Every group of data which is noticed here, for example, this group of data has a particular mean with respect to the machine number. This group of data will have a mean with respect to machine number 6, and this will have its own distribution which will represent the source properties. Every point will have its own distribution, and that will define its source. Now what our aim is to see whether one mean is different than other means. So as the overall average which we have calculated, this is referred as y dot dot. Now this will represent as y bar 1 dot. This will represent y bar 6 dot. So there will be one value which we call it estimated value over here, or average value over here. So there will be a difference which we have to compare with respect to the values given as an average. So there is a difference which is an overall difference. There is a, suppose I consider this particular value. For this particular value, there is one difference with respect to regression or mean of the value, and there is another difference which is with respect to the overall. So this point is, for example, y 1 1. So this is what we call real observed value. This real observed value is y, which will have a difference with respect to y bar, overall value. This will have a difference with the estimated value or y1 dot value. This will have this y cap 1 dot may have a difference with respect to overall average. So there are three differences which we see here. Now this one will be called as overall deviation. This will be called as deviation due to the change in machine, or what we generally called it treatment value. So this is a change which we are seeing for the machine. What is left over here is nothing but we call as error or unexplained variation. So all these three, 1, 2 and 3, all these three are three types of variances. And here the point of hypothesis testing starts. So basically what ANOVA does is looking up the difference of this unexplained variance with respect to this explained variance. Explained variance is because this is a level here, so difference is this, level here, difference is this, level here, difference is this, level here, difference is this, here and here. But these are differences which are explained with the reason that the machine number is changed. But this difference is unexplained. For every value the difference is this one, for this value the difference is this, for this value difference is this one. So this is unexplained differences. So basically there are two types of variability. One is the variability which is created due to the change in the number of the machine, and there is another variability which exists as a matter of fact of randomness in any of the system. So we have to compare these two variances so that we can know whether the variability caused due to machine change is significantly different than the generally randomness or not. That is what is possible when we apply F-test hypothesis. That is the backbone of ANOVA analysis. So in brief, I will just walk through the F-test hypothesis and then I'll come to the ANOVA. So there are two variabilities here. One is sum of squares of treatment, that is sum of square of treatment, that is summation y bar I dot minus y bar dot whole square. This is the variability due to sum of square of treatment. Then sum of square of error, that is the variability due to the randomness, which is nothing but summation variability between y ij minus y bar I dot square. There will be two summation I and j. I represent treatment and j represent your replication. I am taking the concept of one-way ANOVA first. So what happens when we have to find out F value calculated will be variance of treatment square upon variance of error square. So variance will be nothing but sum of square of treatment upon degrees of freedom of the treatment upon sum of square of error upon degrees of freedom of error. Now in this way we can see how we test this hypothesis over the F distribution. If suppose this is an F distribution and I fix a point of criteria here, decision criteria, let's have so this will be critical zone where you reject your null hypothesis. Null hypothesis assumed is S of treatment square is same as S of error square, means both are the same variances. So this is critical zone. When we fix critical zone, we fix the type 1 error as alpha, which is 0.05. So if alpha is 5, we find out the F value from table of F distribution, and that will be F alpha new treatment comma new of error. Now if our calculated value, which is this one, is falling in this zone, so this is your acceptance zone, we call H0 accepted or not rejected. It means that there is no effect of machine. All machines are producing the same kind of rubber having the same tensile strength. Although if you are getting a F calculated value in the critical zone, somewhere lie here, for example, where the p value is less than alpha, or F calculated is more than F table value. Here F calculated is less than F table. Here F calculated is more than F table value. This is F table value. This is F table value. Then in that case H0 rejected. If H0 is rejected, it means that the machines are not having the same output. So there is significant effect of machine, and at least one machine is different. We don't know how many out of 6 are different to the other ones, but at least one is different. So this was the basic philosophy of F test behind ANOVA analysis. Now, to understand what the ANOVA analysis will be simple for you with taking the same example as I have given to you in the beginning, and I will explain step by step what to do when we are performing ANOVA analysis. So take the example of one-way ANOVA and we'll move further. So now this is what the hypothesis is, where we assume the null hypothesis that all means are same. All means means all means of the tensile strength of each machine is same. This is what we assume as null hypothesis. Now our target using ANOVA is either to reject it or not reject it. If we are not able to reject it, it means the machines are not different. Or the alternate hypothesis is that at least two of the machines are not producing the same result. When we talk about the model equation, so here the model equation says that the real observation has the mean observation with respect to each machine and error. This mean observation, if we take overall mean as an out of that mean observation, then this is alpha I. Alpha I is nothing but basically y bar I dot minus y bar dot dot. It is representing this term, and this is representing y double dot bar. So, and error is representing y bar I dot minus y ij. So these are your variabilities as I had already discussed with you. So this is the model equation which assumed for one-way ANOVA analysis. We have presented the data. I have already explained. This is total values with respect to each machine and the mean values with respect to each machine. And these are all observations, all replications. So what we see here, N is N replications and K machines if we compare with our problem. Now what I have explained is presented over here. This is total variability, real observation minus the average of overall value. This is total sum minus sum of the treatment. This is what I call sum of a square of treatment. This is sum of a square of error. This is sum of a square of total. So now what will be the degree of freedom? So there are n into k observations. So total degrees of freedom will be n into k minus 1, which is nothing but given over here. And degrees of freedom for treatment is, because there are k treatments, so k minus 1. So sum of variance of the treatment will be sum of square of treatment upon k minus 1. And sum of square variance of error will be sum of square of error upon what remains, this minus this, equal to this. So it will be k into n minus 1. So when we compare this, there will be f. F is nothing but sum of square of treatment upon sum of square of error. Our final ANOVA table, where we write in this format. First column represents sources of variance, source by which variability occurs. So it is treatment, that is nothing but our machine. This is error, common randomness assumed in the output. So this is sum of square of treatment, this is sum of square of error, this is total sum of square. Degrees of freedom for treatment, degrees of freedom of error, and total degrees of freedom. This is the variance which we assumed here, sum of square divided by degrees of freedom, sum of square of error divided by its degrees of freedom, which gives us an F ratio as mean sum of square of treatment upon this is written slightly wrong over here, mean sum of square of treatment divided by mean sum of square of error. That will give us the value of F calculated. So this will be calculated value. With respect to calculated value, either we can pick up p value from the table, or we will see whether p value is less than alpha or p value is more than alpha. This will be decision criteria, or the other decision criteria is F calculated is more than or less than F tabulated. F tabulated is F value at a particular value of alpha for nu of treatment, comma nu of error. Nu of treatment in our case will be 6 minus 1, so it will be 5. Error will be, because there are 4 number of replications, so 6 into 3, it will be 5, this will be 18, and that will be 6 into 4 minus 1, 24, minus 1, 23, so the sum is 23. No problem, alpha is assumed as 0.05. So with respect to 0.05 table of F distribution, we can pick up this value from the table, and that value will help us to make the decision whether machines have significant difference on the rubber strength or not. So this is the decision criteria. I have written it slightly summarized form. Look at the examples shown over here. This is the example on which we will work, and we will create the ANOVA table, and that ANOVA table will let us exactly know what is the effect of machines on tensile strength. The whole procedure which I have already explained to you, I will do it in Excel, and then later on in the same lecture I will do it using SPSS software. So you will know both the procedures. Excel is more like you are doing it using pen and paper, and SPSS will be more like you are doing professional research analysis. So it will help you both the ways. So start from the Excel, because it will explain you the basic procedure of ANOVA analysis. So this is our table. I will copy it to another sheet. Let's have it here. So what do we want? We want the total value, and we want the mean value with respect to the equal to sum is this sum of all these cells will be equal to 688. Pull it down there. Is the value of the sum. Now what will be the value here? It will be an average of all 4 values. So this will be average of these divided by 4 will become your y values. Now if I take overall mean, So that will be the mean of average. There are two ways to calculate this. Either take average of all these values or take an average of these values. So I take the average of all the values just to avoid the confusion. Let's have it a number. So reduce down the values. So this is your overall value. So what are these? So this value is y1 dot and this value is your y bar 1 dot and this value is y bar dot dot. So if we know this, we can find out escape. It is better if suppose we find out y I dot minus y dot dot. So what it will be? This minus this, and because we have to keep this constant, so we will put dollar here and dollar here. This will be the value, and if we pull it over this will be the term. Now what will be sum of the square of this is equal to n is 4 multiplied by sum of now the square of treatment variance. So it will be equal to this multiplied by the same term into that will be over here. So now what will be the total sum of the square of treatment is 4 multiplied by sum of all these values. If I have to find out sum of a square of, to do sum of a square of error, first of all I have to find out yij minus y dot dot, and that is the term equal to this minus this term. I'll put a dollar here to make it constant term, dollar here. Okay, I'll pull it 6 column, 4 rows. Now this is now square of this, the square of error will be equal to this multiplied by this, and that we have to pull over 6 column and 4 rows. What will be sum of the square of error? That is nothing but summation of all these values. All these values. Now using this we can generate ANOVA table. ANOVA table. The first column is source of variance. Second column is sum of squares. Third is degrees of freedom. Fourth is mean square, and fifth is F value. Sources of variance, sum of the square of treatment, nothing but we call machine, then error, which is sum of the square of error, then total, sum of the square of total. What will be the treatment sum of the square? 533.83. Sum of the square of error is 6797.83. 2.83. Now total will be nothing but equal to sum of these two. What will be this? Error is 5 and this is 18, this is 23. Mean sum of a square, this is equal to this divided by this, and the same for the sum of a square of error is this. What is F value? F value is nothing but mean sum of a square for machine divided by mean sum of a square for error. Now this is your F value. Now we have to see whether this F value is, which is a calculated F value, is less than or higher than. Now see the F distribution table for the value of alpha as 0.05, where nu1 is the degrees of freedom for the treatment, which is nothing but 5. Nu2 is degrees of freedom for the error. So for the value of alpha as 0.05, nu1 as 5, this is the column, and nu2 as 18, this is the row. So where it intersects, we find the value as 2.77. So this is what we call F tabulated value for alpha equal to 0.05 and nu1 as 5, nu2 as 18. The value which we have calculated is 0.28. So what we see over here is F table is 2.77 at alpha equal to 0.05, nu as 5 and nu2 as 18. Now F calculated is 0.28. What it means that F calculated is far less than F table value. So what we see over the F distribution, this is your F table value, and your F calculated will be far over here, somewhere here 0.28, and F table is 2.77. It means that H0 is not rejected. It means that all the machines are producing the rubber stamps of same tensile strength. That was our decision out of the ANOVA analysis. If it could be the case that F value is more than the critical value, then only that case we can say that H0 could be rejected. In this case, we are reaching to a particular decision point that all the machines are producing rubber stamp with the same mean strength. The variability accounted by the change of the machine is not significantly different than the normal variability in the output, the overall variability in the output, which we call error, variability of error, or sum of a square of error. So that is what we see. Now in a very short view, I will show how this ANOVA analysis, how this problem can be solved using SPSS.
This is the same problem which we have done using Excel. Now I will explain how this problem can be solved quickly using SPSS software, because most of the research scholars are using SPSS. So now let's open SPSS. Now we have to type in data, because we are going to make a new file. So this is SPSS. Now there are two windows. One is data view, another is variable view. Our first variable is machine numeric, but if we want it to be a machine cannot be a numeric value, so we can have it a string of 8 characters. So now here I can type machine 1. See, we had in a matrix form, data was in matrix form, but here we want to have data in two columns representing two variables, because these two variables will be considered as one independent variable and the other as dependent variable. So machine 1, let's have M1. So we have now there are four set of values. It is very important in SPSS how you place the data before the analysis. So actually we are doing ANOVA analysis. We are not doing pairwise t-test between different machines. So if we were doing t-test, then we had to take the same table of the data. Every column could have represented machine type. But here, because we are going to perform ANOVA analysis, so we are going to have the data in this way. So first column, go to SPSS, paste over here. Now we can paste data for second column. Now we have these two columns. If we see in variable window, one is machine, the other is tensile strength. Now see here, go to analyze. If we want to see the spread of the data of the tensile strength, we can see descriptive statistics. Go to general linear model, go to univariate. Dependent variable is tensile strength. Pick here, machine is our fixed factor. On dependent variable, there is no random factor, there is no covariate. If I want to see the plot, machine versus tensile strength, I can see over here. Continue. If I want to do an analysis which is called as post hoc analysis, which gives us a difference between each machine, I can select one of that analysis. Suppose strain demand cools. Continue. I press OK. There is an output window visible to us which gives us, oh, coming analysis is coming for data for machine 1, and it ensures that the data is correct. Now if we see the ANOVA table, first is interrupt set model, don't care about this. Machine, this is our variable machine which gives a value of f 0.307. When we should remember that the value which we had calculated was 0.28 something. So it is very close to our calculation. We are fortunate that we have got the correct calculation using Excel. This was that, and now what we see the significance value or p value, we call it as 0.9, which is far more than 0.05. So the calculated value is far less than the value of table value, a value at particular value of alpha 0.05. So this was what was the ANOVA analysis, from where we see that if this value would be less than 0.05, then only we could say that analysis machines have significant effect on tensile strength. But in this case not. In post hoc analysis, all machines shows a mean value which is almost similar, and not similar, then also the spread of the data will be very same, which we can see over here. This is the data, but it is not significantly different. We can change it and see how this difference is. We select this axis, we modify the axis, scale, first value, suppose I make it 0, and then I see how data is. See, data is quite flat in nature. So it means there is no significant change due to the change of the machine. That is what I wanted to say using SPSS, the same thing I did in Excel. If you want to save file, you can save as output, which will be SPB, and your input can be saved like this. You can save to the location wherever you wish for. Suppose my location is, you can save as SPSS. Same file I can export as Word file if I want to. The same location it is showing, so I can save as the Word file. So I have my data in my hand. There is another way of doing this. Open a new file. Suppose the data was here for 6 machines. I pick up all the data and I come back to SPSS, new file. I place this data over here, copy paste. I go to Analyze, I go to General Linear Model, I go to Repetitive Measure. In Repetitive Measure, every row is a kind of replication and every column is a label of the independent variable. In our case, independent variable is machine labels are 6. I can add that. Sphericity is nothing but testing whether the data satisfying the assumptions for repetitive measure analysis. So I'm not going in more detail of not least test of sphericity, but what we see here is again the F value calculated is 0.291, slightly different than the other procedure, which also indicate that machine has no significant effect on the tensile strength of the rubber stamp. So this is also you can save as, or you can export this data to the same location as output. As output, I can refer as
maybe a quite lengthy lecture, but it was required because if I move on to other kind of analysis in forthcoming lectures or other kind of tests, then this basic understanding of ANOVA is important. That's why I took a little longer time this time and not the next time. Thank you very much. Don't forget to subscribe if you like it. Thanks.